so last time we talked about how to discriminate between two different stimuli, two different odors, in this case in the olfactory system. One hypothesis or one group of hypotheses are that we determine it by the precise timing relative to the sniffing cycle of the animal. So the animal continuously sniffs in cycles, in these theta rhythms, and each neuron will spike in a specific phase of the sniffing rhythm, and the precise signature of the odorant is determined by the precise spiking at the phase of the sniff, and this has been shown by the Hopfield model to at least account for the concentration invariance. Okay, so this was one thing we talked about. Last time I rushed over the second pool of hypothesis of people that claim that what determines between one odorant and another is not a single neuron response, but rather the population code. Specifically, two different populations will have very similar response profiles to two specific odors, but with time, the spiking patterns of the two different populations will decorrelate over time. This has been persuaded strongly by Gilles Laurent and colleagues by studies done in Locus, many series of Nature and Science papers in the computational field. This is just one major example done in fish, I think, in the fish olfactory bulb, and you can see two different odorants, and these are just different neurons and how they respond to these two different odorants. And in the first 100 milliseconds, you see that the patterns are very similar, the correlation is high. So for a decoder outside the network, it would be hard to differentiate this pattern of activity of this neuronal population from this pattern of activity. Okay, this is real data. Okay, so this would be calcium imaging in this case. Okay, which they translate to firing rate. But with time, after 300 milliseconds, the populations no longer resemble one another, and this goes on, and after a second, these populations of neurons are highly decorrelated, and therefore a decoder outside of this network would have an easier time to differentiate the two different odors. So these are the two main streams of communities, and this is highly debated still. Okay. One thing that I wouldn't say poured cold water on this phenomena, and I mentioned this last time, is that people started to do very serious psychophysical experiments, behavioral experiments, measuring how long it takes an animal to differentiate between two odorants. And what they find is that within 200 milliseconds, the animal has already made a decision long ago. So everything that comes after 200 milliseconds is not that relevant to the discrimination decision of the animal. Okay? And then the people from this community started to show that indeed, even within the 200 milliseconds, there is decorrelation, and that is an important computation or a decoder. This is an important thing that we would look at. Okay? So the debate is still on. There was just a Nature Neuroscience paper, 3 months ago, exactly doing this in mice. But I want to show you the other side, the ones that claim that mice are fast, because it also used to be considered a very slow sense. Odors, chemicals are flowing slowly, certainly not as fast as light or sound. But in fact, when you look at perceptual decisions, these animals are as fast in making perceptual decisions as they are in visual decisions, in olfaction as they are in visual decisions. One elegant example is this paper by Di Marimberg and Matt Smear at the time in Genelia. What they did is they made a mouse which has an OMP channel rhodopsin connected to it. Okay, this means that each and every olfactory sensory neuron in the epithelium will have channel rhodopsin. Okay, all the epithelium will have channel rhodopsin. And what they do here is they implant a laser into the nostril, and they can play different patterns and different lights, okay, and test whether the mouse can detect the light activation as if it was an odor. Okay? Basically what they do is they teach the animal the task with an odor to discriminate between two different odors, and you can see that they are doing very well, over 90% success. And then what they do is instead of playing an odor, they play some kind of a pulse here, a laser pulse, and the animal initially it's a little bit hard for the animal to learn, but on the first session, but later on, very fast they become as good in discriminating some random pattern of activation of the olfactory sensory neurons as they are to given odors. Okay?
Is it optic activation of the neuron?
Yes. So there's a laser in the nostril of the mouse.
Okay.
Okay? Yeah.
Do they limit the pattern of activation?
No. So this is just a random, okay, and you can teach, that's very easy. In fact, it's very easy in general to teach an animal to behave according to some spiking pattern, even in cortex, etc., but they do this in the nostril. Okay, in this case, just to mimic the odor. The nice thing about this system, about this paper, is that they show that the mouse has perceptual access to the phase of the sniffing cycle. And they do it in the following way. They measure with the laser, they put a probe in the nostril, a pressure cannula, that measures the precise sniffing cycle of the animal. Okay, every time it inhales and exhales, you can measure the sniffing cycle online, as it happens. And the beauty of optogenetics is that you can do it fast, okay? It's on very fast sniffing times. So this would be the inhalation, and this would be the exhalation of the air. So this is one sniffing cycle, and an animal normally sniffs 3 to 5 hertz or something like that. Okay, an awake animal. Sometimes they go high in sniffing if they're very interested, but generally this is the rate. Okay, so the whole window is about, I don't know, the full sniffing cycle is about 300 milliseconds or so. 200, 300 milliseconds. What they do here is they give them two different pulses. Two pulses. It's the same pulse of light, but which comes in at different times in the sniffing phase. So the go signal for the animal, the behavioral signal to go, is 32 milliseconds after the inhalation cycle. So they're coupled. Once the animal sniffs in, they give a laser pulse. Okay, that's the go. And the no-go signal comes, in this case, 32 milliseconds after the inhalation stops, so within the exhalation cycle. And quite remarkably, the animals, it takes them a little bit of time, okay, to learn what's right and what's wrong, but they can differentiate this signal from this signal. So it is exactly the same neurons that fire, because it's the same flash of laser, but it comes in different phases of the sniffing cycle. Okay? So at least they have perceptual access to what's going on within the sniffing cycle. And again, Dima and colleagues are one of the major contributors to this theory that what discriminates different odorants is the exact activity within the sniff cycle. Within the sniff cycles. What they did here is that they left the go signal intact. Okay, now they pushed the no-go signal to here. That's 200 milliseconds. Normally an animal will do it within two different odors, will do it 200 milliseconds. They can do as good as they do odors, 90%. And then they push it to 50, you see the performance goes down. This is what you saw before here. This is the 32 milliseconds. They'll still be able to do it. I think it's the 32. Anyway, so they push it, maybe it's not exactly the same thing. Anyway, they push the no-go signal towards the go signal to see what is the resolution, the perceptual resolution of accuracy. And quite remarkably, even 20, 30 milliseconds after the first pulse, the animals can still do statistically better than chance. This means, it doesn't mean that when you sniff odors, this is actually the information, however, that you're using. However, force the animal to the wall to see whether it can have perceptual access to this kind of resolution, it does. And this is 50 milliseconds, okay? And this really exemplifies beautifully the power of optogenetics, okay? And mouse genetics as well, and psychophysics, and all beautifully integrated into a theory of order detection. Question?
And the two, the go and no-go, are random, but different signals, right?
No, it's the same signal, it's the same pulse of light, but it's just coming at different times of the sniffing cycle.
And it's the same signal exactly?
Same neurons, exactly.
Yes, the same frequency of signal, same
Yeah,
pattern
just
of-
one pulse. I think maybe not one pulse. This, the signal is a series of stimulus interval, laser pulse. Yeah, one or two laser pulses in the sniffing cycle. Okay? So it's the same neurons, but they fire in a different time in the sniffing cycle, and that's the argument of the people, that in fact if you have an odor that comes in and the neurons spike at a given phase in the sniffing cycle, it will signify a different odor. That is the signature of the specific odor within the sniffing cycle.
But what would reduce this difference between the time and the cycle?
What would produce?
Yeah, because if I...
So this is exactly what we talked about when we talked about the Hopfield model here. Okay, so that is like the foundations of the idea, and we talked about it last lesson. Each individual microcell has some bias in the glomerulus. The glomerulus has also a bias to specific odorants. Okay, and this is what we saw from the days of Linda Bach, when she looked at the olfactory sensory neurons in the plate. And together these will determine which part of the sniffing cycle the microcell will fire. Okay, so if the threshold is lower and you push this iceberg effect, you push the membrane potential. If you push it higher, the neuron will spike with an earlier latency to the odor.
But what we saw now was in the epithelium, not in the microscope.
Yeah, it's fine. It doesn't matter. First of all, they also repeated the same experiments later on in the shining light in the olfactory bulb. But it doesn't matter. The proof here is that the animal has perceptual access to the information in the sniffing cycle. Okay? That's the beauty of this Nature paper in this case. Okay, by this we more or less finish the first station, or the second station. We first talked about the epithelium, and now we talked about the olfactory bulb. And this is yet another schematic of what you saw. On the top is the epithelium, this is the olfactory bulb, and now the axons of the mitral and tufted cells, they go to the next stations, okay? Higher brain areas. And where do they go? They go into 5 different regions. Loudly, we divide them into 5 different regions. The first one that they go to is they make a cross. They go to the anterior olfactory nucleus. The anterior olfactory nucleus actually then crosses to the other side of the olfactory bulb. So there is information between left and the right nostril. The question is, why? Why do we need information to flow from the left to the right nose? What would be a prediction? The?
Direction of the sound.
Okay, so maybe we can localize the direction in space. When we will learn about the auditory system, we will exactly see how amazing the auditory system, is in localizing sound in space. Okay, that's my next lecture, or not the next, my third lecture from now. And that's the idea. We don't really know. Animals are not that good at discriminating. Okay, if you close your eyes, I tell you if the odor is slightly to the right or slightly to the left. It will be very hard for you to detect. But that's the main idea. There was a big paper in 2006 entitled "Rats Smell in Stereo." So there is the stereo smell. It had some problems. This paper had some small issues in it. We're not going to go into it. But later, the same authors had a nice paper from 2013 doing imaging in a lateralization test. Okay, so basically the animal has to poke into it's the snout into the odor stream, and sometimes the odor comes from the left and sometimes the odor comes from the right, and the animal can detect this. So they can show that behaviorally the animal can easily say if it's coming from the left or from the right. And what they show is that there is this lateralization of activation that, so first of all, there is symmetric, okay, it's highly symmetric. However, the timing, so these are the two olfactory bulbs, left and right, left and right, left and right, left and right, left and right. This, I guess, are timings on the top, but you can see that initially if the odor comes from the right, you start to see glomerular activation here, and they become stronger. So the pattern of activity evolves earlier in the left side of the brain, of the olfactory bulb, and later on starts to appear in the other nostril, in the other side. Now this is just shows you the complexity of the system, okay, of how does the spatio-temporal pattern of activity evolve in the brain, and it can evolve. There's also information coming from the two different nostrils. But we don't know much about lateralization in olfaction. Like I said, animals are not extremely good at that. Although if you do go to the, what I showed you initially, when we started this long time ago, 6 hours ago, you remember that the animals can do tracking pretty well, okay? But what is the resolution of left and right? We know very little about this computation in the brain. As usual, we do know something about this computation from flies, okay? And in fact, in flies there is a very nice mechanism of this, and that's a little bit different. In mammals, the axons go to one side of the brain, to the bulb, and then go to the AOM and then cross to the other side. There are a few synapses. In flies, each olfactory receptor neuron sends its axon to a specific glomerulus, but on both sides of the central nervous system. Okay, so the axon splits, and they make an axon on the two sides of the brain directly from the olfactory receptor neuron. And the question is whether the animal can lateralize, say in space where the odor is, and if so, what is the mechanism? There's a beautiful paper by Rachel Wilson showing first behaviorally that you can train flies to go left or right. Okay, so this is the behavior of the fly. It just measures if they start to crawl to the left or crawl to the right, and she can easily train Drosophila flies to go left or right. And what's nice about this, again, as usual in the fly system, which is, she can record from the presynaptic olfactory receptor neuron its cognate projection neuron on the same side, and also from the cognate projection neurons on the ipsilateral side. Okay, the contralateral side and the ipsilateral side. So the ipsilateral side means, you know this term? You're on the same side. The contralateral is on the other side of the brain. Great, so she can make, dual recordings simultaneously and excite this given ORM with the others. What she sees quite remarkably is that there are changes in the timing, in the very fine timing and synaptic release properties of the same axon of the same neuron if it's on the contralateral and ipsilateral side. Okay? So if an odor comes from the right, I will have a stronger synaptic activity from the same neuron initially on the left side than on the right side, and there's already built into the system this type of information by the synaptic release. We're not going to go into this mechanism at all. I'm just telling you, all you need to know is where is the information going from the olfactory bulb to next stations. Okay, so the first station is the AOM, and it's probably in order to lateralize and detect odor in space. Detect where are the odors in space. We know very little about this. Very little. Okay, as we speak, I would guess there are a handful of labs testing this kind of a thing. The other information, perhaps the most dominant target of the olfactory bulb is the cortex. This is the piriform cortex, the olfactory cortex. The olfactory cortex is different than the neocortex. It's not part of the neocortex. First of all, you see that it's getting direct inputs from the olfactory bulb. Other cortices, the neocortex, there's some relay stations, thalamic relay stations specifically. Also, if you look at this, the piriform cortex, it's unique because it's not a 6-layered cortex, it's a 2-layered cortex. So it's a very primitive cortex evolutionary. Okay? So it gets the information from the piriform cortex, and there are a few interesting things that occur here, which are a bit related to the papers we're going to discuss next week. Okay, so the first ones who describe the responses, not the first ones, but the nice relatively recent papers, 6 years ago, 7, to describe the responses of cortical neurons was by Isaacson, Jeff Isaacson and colleagues at UCSD. Jeff is still one of the main leaders of piriform cortex physiology. And what they did here is simply record the neuronal responses to, in this case, 4 odors. Okay? Sin, AA, lim, and phenyl, whatever. Okay? Now you can do what other people did, is ask a single neuron what is the receptive field by patching this neuron and then playing 100 odors. Or you can do the other trick around, is to record from many neurons, but play only very few odors. So this is like the mirror image. It's not as complete, but it's another strategy which he used here. So basically, he's recording from, in this case, you can see 4 neurons, where he records the spiking activity, and he plays this odor, this odor, this odor, and this odor. Where you see the magenta color, it means that it was statistically significant. So cell number 1 responded to this, cell number 2 responded to this odor, and cell number 3 and 4 responded to 0 out of the 4 odors. And in fact, when you look at all the population, you see that 70% of the cells did not respond to any odor. 20% of the cells responded to a single odor. Very few responded to 2 out of the 4, and most of the cells, and very few responded to, had wide receptivity. So the belief is that neurons in piriform cortex are rather sparse, respond to very few odorants, and they're not very dense in their responses. Okay? And in this case, they didn't find some preference to one of these 4 odorants. So that was one of the main findings of this paper. The second finding of this paper is that this is when looking at spiking activity, so recordings was extracellular. But in the same paper, they have a section where they do whole cell recordings. And in whole cell recordings, you can extract both the excitatory input to the cells and the inhibitory inputs to the cells. Okay? In general, as you should know by this time in neuroscience, each neuron, most of the neurons in the brain, most of the neurons in the brain receive a barrage of synaptic excitatory inputs, but also a barrage of inhibitory inputs. And it is this delicate balance between excitation and inhibition which is critically important to the activation of the cells, in general in the circuits. Okay? We, in fact, saw that the olfactory bulb circuit is dominated by inhibition, by many types of inhibitory neurons. In cortex, there are a handful of different inhibitory types, depending how you categorize them. Some would say 12 different types, but nevertheless. Okay? But this balance between excitation and inhibition is quite important. And what you see here, these are inhibitory currents of the same cells responding to the 4 different odorants. And these are the excitatory currents. You can do this by patch clamping the cells at different voltages. And what you see is that, for example, for this odorant in this cell, that it receives slight excitation and quite robust inhibition, which is in fact also locked to the sniffing cycle in this case. The same cell will have very weak excitation for this odor, still strong inhibition. Small excitation, strong inhibition, strong inhibition. And in fact, what we see is that the inhibitory drive into the cell is rather wide and robust. Almost any order that he played, okay? Almost any order that he played, over 50% of the cells, or about 50% of the cells, receive inhibitory drive from the 4 orders in his panel, as opposed to the excitatory drive, which is received by very few orders in the panel. Okay, and this means the meaning of this is that if you look at the circuitry, is that the axons that are coming from the olfactory bulb provide very strong inhibition. Particularly, they do not make inhibitory connections. Those that microcells have glutamate in their axons, so they are excitatory neurons. They provide strong synaptic inhibition through the inhibitory neurons in the peripheral cortex. So the inhibitory cells actually receive inputs from many odorants, and the excitatory drive is only from a much fewer or a narrower wind of stimuli in the previous neural circuit. Yes.
So mutual cells just fire every breathing circle, every breathing.
What? The
mutual cells.
The mitral cells, yes, they have very high activity levels. Actually, we'll also see it in the paper by Wilson in Drosophila. And I think I will show you again, but when we looked at the MOE model, you saw this, okay? So every breathing cycle, I told you about the rhythm of life, you remember. So when you hear these spikes, you hum. When you put an electrode into the brain, in the cortex, it's boring. And you play a sound, you show a movie, and you see spikes. Actually, in the visual cortex, it's quite nice when Hubel and Wiesel saw this, you get serious spiking. Auditory cortex is quite silent. But here, if you put it in the bulb, many spikes, very serious, very sniffy. So, this is the model of the cortex. That's 2009, and 2011, there were 3, not 1, not 2, but 3 back-to-back papers in Nature showing exactly the same results by completely different methods, showing the anatomy from microcells to the cortex. Okay? So again, this is 2011, and this is as basic as it gets. The first authors, I'm going to show 2 papers. One, of course, by the Richard Axel group. Okay? I think this, yeah, by Richard Axel group, Solsky and colleagues. What they did is they simply injected dye into a single glomerulus in the microcell, in the bulb. That's it. And they looked at the axonal profile of the microcells that come from a single glomerulus in the olfactory bulb. And what they found is this image, which you will see now in many textbooks. It's quite remarkable. So this is axons of about 25 microcells. Okay, normally axons, one thinks it's a small entity. It's 2016, and few people really reconstructed full-blown axons of neurons. But when they did, they are humongous. Okay, axons are they can spread. They're very, very thin, but they can spread into many regions of the brain. Generally speaking, okay, this is true anywhere in nose, in projection neurons. And these are the axons of the microcells that come from a single glomerulus. Okay, so if you look at the olfactory bulb here, one glomerulus, and there you have the, about 25, 30 or so microcells sending a dendrites in, and these guys is what you see here. This is the axon terminals of the microcells that come from the bulb. And what you can see quite remarkably is that the axons that come from a single glomerulus spread out in wide range regions in the peripheral cortex. So these are on the top is the peripheral cortex, this is the amygdala, this is the entorhinal cortex, getting a little bit, this is the lateral olfactory tract, this is the olfactory tubercle, this is the AOM. We talked about that. It's related to the other olfactory bulb. Okay? So just this amazing image, which can be a poster on its own right in a museum or something, but just this image tells you that there is very strong divergence of axons into the piriform cortex. In fact, in the amygdala, you see that axons are not diverging, and they are, as you can see, are residing in specific regions in the amygdala. A little bit like we saw in the flight. Okay? We talked about the flight. So this would be the injection. Okay, so you can make animals with axons expressing GFP from the olfactory epithelium, and now you inject only in that specific glomerulus, rhodanine, and this is how it looks in the olfactory bulb. These are the microcells of this specific projection, or maybe this, I don't know, but all the neurons connected to a single glomerulus are expressing this stuff. Okay, so this was one of the three back-to-back papers in Nature showing the very strong divergence from the olfactory bulb to cortex. The other paper was a transsynaptic paper, rabies transsynaptic tracing, from the lab of Li Xianglu, which is my colleague, and these are methods that we're now using we have imported in the last 5 years to go back to perform them here in Israel, which are finally working after 5 years of tweaking. But nevertheless, what you can do in rabies is that you can have starter cells and then label the presynaptic landscapes of these neurons that were labeled. So what they did, what Kazunari Miyamichi did in the 2011 Nature paper, is to label starter cells in the piriform cortex. Okay, so this would be part of the piriform cortex. Okay, so you start backwards. Instead of going antrograde from the bulb to the cortex, they labeled neurons in piriform cortex and looked where are the presynaptic partners of these cells. So they go back to the olfactory bulb and ask where are the neurons reside. One option would be, let's say now I'm labeling neurons from a single neuron in piriform cortex, is that all the neurons will be microcells belonging to one glomerulus. Maybe they can be spread all over the place. Maybe they can be, allocated in specific regions, etc. And what they find is exactly complementary to what Axel found. So they start to trace from piriform cortex neurons, and they reconstruct in the olfactory bulb where are the presynaptic neurons. These are three-dimensional reconstructions of full olfactory bulbs. Each dot here, I think, is an experiment or something like that. And you can clearly see, this is from piriform cortex, this is from amygdala. And in the piriform cortex, you can clearly see that these are distributed all along the olfactory bulb. Okay? So neurons from piriform cortex come probably from different glomeruli all along the olfactory bulb, and we can see no clear rule that governs here. Yeah.
So in CND you see connections from one neuron in piriform cortex or one area?
So it's normalized, but for the argument today, yes, let's say yes. Okay, it's a very small number of neurons. And in a few cases, they do have like 2 or 3 starter cells or something like that. It's very difficult to get only a single starter cell. But the main idea from doing these the statistics on these types of experiments is that from piriform cortex, input is coming from many regions in the olfactory bulb, while in the amygdala there is skewness to dorsal regions in this case. Okay, you can see also in this picture that the ventral side of the olfactory bulb doesn't have as many cells, and there's more information in the specific regions of the olfactory bulb.
I don't remember if this was mice or something else that we saw this division of the olfactory bulb. That some mice are more localized dorsal part. So, what's in the dorsal part there?
The dorsal part, we talked about that, are this TMT odors and odors that are frightening to the mice. We will get to it when we look at the actual paper. Yeah, you still remember we had the Ynet science article about the mice that are not afraid from cats. So when we talked about this here, because when they actually killed all the glomeruli from the dorsal surface, they deleted the innate factors, and basically this is the slide you're looking for. Okay, so the dorsal are the amines, fatty acids, and these fox urine, so some innate and some food odors, things like that. Okay. So, where are we? Here, okay, so this is the quote from the paper. These data indicate that highly restricted area in the piriform cortex receive direct microcell inputs representing glomeruli that are distributed throughout the olfactory bulb with no apparent spatial organization. So from the very punctated, nice spatial patterns, we're now losing everything. So the brain put a lot of money and effort in order to build a brain that is nicely organized, all the axons coming into the glomeruli, but at the next step, the next synapse away, it's completely divergent. Okay? And this is the scheme of the olfactory bulb to piriform cortex. So microcells from different glomeruli in the bulb will probably innervate specific piriform cortical neurons, and single neurons from a given glomerulus will distribute into many piriform cortical neurons. Okay? And we will touch upon a little bit about the computational power of this divergence and convergence in the papers that you are reading for the sample. Okay? Again, in the Rachel Wilson paper. But this is, again, a very general problem in computational neuroscience. Okay? We don't really understand what are the advantages and disadvantages to diverge or converge information. I mean, convergence is a little bit more intuitive because it's, it will increase the signal-to-noise ratio, the contrast, it's a little bit more intuitive. But all these designs of diverging, converging are very basic building blocks of the brain which have computational significance that we do not fully understand. Okay, that's why we pay you the big box to be computational students and tell us what are the advantages of divergence and convergence, etc. Okay, the next paper I want to talk about is also recordings from piriform cells. Now this is electrophysiological recordings from piriform cells, utilizing the power of optogenetics to flash light in the olfactory bulb. Okay, so you can take one of these projectors, like it's projecting this slide, which has many mirrors that you can play separately. You can shine the light on the olfactory bulb and start to play patterns of activity. People started by drawing their names on the brain, activating microcells, etc. But eventually you can take this laser, take a channel rhodopsin expressing mouse. In this case, it's a mouse expressing, I think, in the microcells, or it can be the ORNs also. I don't remember exactly, but it doesn't matter for the sake of this argument. And you can shine light in a single spot in the olfactory bulb. If you record from this spot, you will get activity of the microcell, which proves that you can actually drive this microcell. Okay, and now you can use your projector to have 2 spots. Great. And 4 spots. And 9 spots. And 16 spots. Mimicking glomerular pattern activation. Okay? Because when we sniff an odor in, we already know that we're going to have specific spatial and temporal patterns which we can mimic with optogenetics. And if you record only from this spot, what you see in the olfactory bulb is that there's not much difference. Okay? In fact, there is decrease in activation when you start to increase neighboring glomeruli. And this is because lateral inhibition that we learned about last time, right? Because if you activate other parts of the bulb, there is some inhibition that comes in, and in fact, this is well-known phenomena which is called mixture suppression in the olfactory bulb. When you mix many, many odors, you actually get reduction in the activity in many cases. And this is probably part of the role of the olfactory bulb in gain control mechanism. Okay? So basically you can drive the olfactory bulb and with activity which doesn't change much. If anything, there's some a little bit inhibition here. If you put your electrode in the piriform cortex, an interesting thing happens. One, if you shine light from a single glomerulus in the bulb, you normally get nothing. You get zip. Okay, no sparks. If you put more glomeruli in, 2, 4, 9, 16, suddenly you start to get activation in the piriform cortex. Okay, so the threshold of activation in piriform cortex is a result of summing in inputs from many different glomeruli, which is very different than what you see here in the olfactory bulb. Great. Moreover, the piriform cortical neurons will activate only to specific patterns of glomeruli that are activated. So it's not like the general drive that comes in. So in this case, they activated patterns of 16 glomeruli. And this is patterns of 16 glomeruli which are intermixed with the other 16, but very different. And in this case, you get nice spiking responses in the piriform, and here you get none. So piriform cortex neurons are sparse. They get massive inputs, but they're activated only in specific combination of glomeruli. So this is, if you will, the decoder of the activity. What exactly determines this, whether the sniffing cycle and things like that, this is all yet to be determined. There are very few papers that push the limits in technology so far like this paper. Okay? This is a 2011 paper. But now Ian has his own lab in Boston and probably doing nice things. Okay, this is all I wanted to tell you about the piriform cortex. The nice thing about the olfactory system, is that it's also going into subcortical or thalamic nuclei, which means that it goes into the business end of the emotional brain, if you will. Okay? This is not to say, although we do sin and say that olfactory is a more emotional sense than other senses. Okay? Some would argue that the smell of your grandmother's dishes is, brings you to tears. Others would, listen to Mozart and get exhausted emotionally, whatever. So I'm not saying that the sounds are less emotional than others, but I am telling you that anatomically, the olfactory circuits go directly to hypothalamic nuclei, which have to do with emotional value. Places like the amygdala. Yeah.
Is this true also for primates or only for rodents?
No, it's true also for primates. Yes. I don't think the circuitry is well known for humans, for example. Also in monkeys, this is not a system that has been well studied in these animals at all. I mean, if you look evolutionarily, non-human primates are losing their olfactory system, even anatomically, and
So how do we know they're still there?
we don't know. We know this anecdotally from psychology studies. People coming from the army, in traumatic from wars, sometimes can't get rid of the smells. A famous story about people who dipped their hands in economica in Javel to stop the thoughts of the war and things like that. So smells can be also in epilepsy and things like that. There are all kinds of auras of smells. It's anecdotally an emotional sense. But again, I want to reserve, we are serious scientists here, so let me reserve all these anecdotes that we don't know much about.
About the connections. You know that there are connections
In the mouse, yes, we know there are connections.
But
In
you don't know
humans,
that
I
it's
think
outside.
in humans there are also direct connections. I don't think we know very well about, the connectivity. Okay, anyway, so this comes from, for example, amygdala, the nicest example of studies in this sort, 2014 Nature paper, again by our Richard Axel, doing all the great work in this field. And what he found is that the cortical amygdala is critical for innate assets. So let me just finish this, give me 5 minutes, and then we'll take a break. Or maybe we'll take a break later. Yeah. Let's do it now. Let's take a break. Yeah. We start at 1 sharp. Okay, so we're in cortical amygdala, right? So olfactory bulb sends input, sends axons also to the business end of the emotions. The nicest proof of that is a recent paper, 2014, doing the above behavioral assay, bioassay. What they did here is they put the mice in a cage, and this cage has 4 quadrants, and they would introduce an odor into one of the quadrants, in this case the bottom right hand side. And they simply measure how much time does the mouse spend in each of the 4 quadrants. And what you can see here is the tracking of the mouse. This is the case when there's no odor in the cage.
Why doesn't it go near the edges?
It does go near the edges.
Or like, why are the lines concave?
Yeah. They make this concave because of the flow, considerations of flow.
Oh, so the cage.
There's actually a suction here. The cage is in this. This is the exact.
Oh, okay.
Actually, mice, they like to be next to the walls more than the center. You see it right here. Okay. So basically, this is the size of the cage, and you can see that mice spend roughly similar regions. They have no real preference when there's no one. When you put TMT, this is our famous component from fox urine, which is when you put this to mice, many of them freeze, so you see much less lines in general because they're afraid, and you can see a clear decrease in the number of visits they do to this right-hand quarter. This is just a naive odor, isoamylopetat, nothing special, and this is an odor which they found is attractive to these mice. This is called 2-phenyl ethanol. And in fact, they did these bioassays to all these odorants in the x-axis here. So each one is a separate behavioral experiment. And what you see on the top is so the y-axis is the performance index or bias index. And you can see that they prefer 2-phenylenol. They also like peanut oil. And another one, you already saw in the Japanese paper that they like peanut butter and that they're afraid from TMT. So there are a few odors which are stinky or whatever to them. TMT, again, is from fox urine, and the thought is that they're afraid because they also freeze. And there are many, many different odors that they are invariant, that they don't care about. They think there's water somewhere here. Maybe. Anyway. Okay, so this is one of a very nice bioassay of these mice. And the question is, what drives their fearful behavior towards TMT and the attractant behavior towards the 2-phenylenol. The claim in the paper is that the axons coming from the microcells to the cortical amygdala are required and sufficient to induce these innate behaviors, both for aversion and for attraction. So this is a central node of activation that is critical for these behaviors. And the way they prove it is with optogenetics. Okay, so they stain all the microcells in the olfactory bulb with a silencing optogenetic activator, halorhodopsin in this case. And when they do that and stick a laser into the brain, into the cortical amygdala, and they do the test of behavior, so this would be the behavior of the mouse towards the quadrant with TMT, when they do not activate the laser. They inject the mouse and everything. When they inject or turn on the light in the mouse, he's no longer afraid, maybe a little bit afraid, but not as dramatic as this. So there's a very clear decrease in the fear behavior of the mouse. In this case, they put the virus, the halorhodopsin virus, in the olfactory bulb and shine their light in the olfactory bulb here. So they shine the whole thing. Okay, it silences it, doesn't fully convince us. But when they put the laser fiber here in the cortical amygdala, they also get this very strong reduction. Okay? When they put their laser in the olfactory tubercle, they get no change in the behavior. I just remind you about all these. Oops, sorry. Okay, so the targets are the AON, the olfactory tubercle, the piriform cortex, entorhinal cortex, and amygdala. And there's the cortical amygdala here, and they put their laser here in the amygdala. Okay, and they also put it in different places to show that it's really this part that matters. So when they put their fiber, they shine light in the tubercle, nothing happens. In the piriform cortex, nothing happens. And in the cortical amygdala, you see this clear shining of light. When they put no virus and shine light, they don't get an effect, etc. This is the whole data. All the mice, they fear, and when you turn on the laser in the cortical amygdala, they fear no longer. Okay? So if you want not to fear in an innate preference test, a good place to make with is the cortical amygdala. Interestingly, they can also stop the attracted behavior to the 2-phenylalanine by the exact same procedure. So when they turn on the laser in cortical amygdala, normally mice would be attracted to the 2-phenylalanine, but this would disappear later on. Okay?
Can I,
Yeah.
maybe I missed it, but it's channel rhodopsin.
This is halorhodopsin.
Halorhodopsin. And it's
So they
inhibited?
silence. What?
It's inhibited. It's silent.
Yeah. Silence.
So
And this shows that this is required for innate aversion and attraction. But they can also do the opposite experiment with a very elegant trick, which we're also trying to use in our lab for the past few years and working not as good as this paper, but nothing we do it as good as Richard Axel's papers. Anyway, so what they do here is that they trap the neurons genetically. You can do that by injecting a virus into cortical amygdala that is activity dependent, okay, based on some immediate early gene, which will drive temporarily the CRE-ER into the system, okay, when you inject tamoxifen. So if you inject tamoxifen into the animal and the neurons are activated by this gene, you can get recombination. And in this case, they put in the virus channel rhodopsin Y3. So you take the virus, you inject it into the cortical amygdala, and you show it, you inject tamoxifen, and you show it TMT. We hypothesize that when the animal smells TMT, there will be recombination in the neurons of the cortical amygdala. And hence, from now on, after this behavioral event of fear, we have access to the neurons that were activated during the TMT, and we can now, at will, shine light on these neurons, bypass the whole TMT thing, and induce fear. Quite remarkably, so when you do the trapping with the TMT channel rhodopsin, just with the laser, you can induce fear. This shows that fear is the cortical amygdala fibers are sufficient to induce this behavior. So cortical amygdala is required for the behavior and sufficient. This is something you rarely see in other systems. Okay? One, there is a very strong innate behavior. The network, the anatomy of the network leads you to specific high-density axons, and by the right bioassay and very elegant genetic and optic tricks, you can convince the animal that the fearful behavior. Quite remarkably, they can also do this with the 2-phenylalanine. So when they do the trapping with the 2-PE, they can induce attraction with the laser itself. Okay? So this is a very elegant example. And when they do it with no odor, the trapping, or with one of these odors that are naive, behaviorally, they cannot get change in this response. Okay? Questions thus far? None. This is basically what you will find in textbooks, although maybe the last 2 hours or so you cannot find in any textbook, so you should stick to the slides. Other places that the olfactory bulb sends axons to is the entorhinal cortex. We know very little about it. We know quite a bit about the entorhinal cortex that connects to the hippocampus and has to do with memory formation, but we don't know much about this direct connectivity. I actually tried to do some recordings in hippocampus with odor stimuli. Was not very successful. There's actually one in Haifa. She's doing a very nice work with olfaction and hippocampus. Okay, and now what we're going to do is talk about more local stuff, things that we have been doing in my laboratory. This will all be through the exam, so don't worry, it's fine. Still kosher, but not nothing you can find in the textbook. Although some parts of this paper you can find in the textbook too. Anyway, whatever. So this is olfaction beyond olfaction. We've made a clear observation, and there's actually quite very nice literature about how mothers, when they interact with the pups, we like this story very much, they use both smells and sounds to interact with their babies, with the pups. Okay? And what we asked in this paper is whether the smell of the pups has an impact on the coding of auditory stimuli. So a kind of a multisensory interaction in the brain. A multisensory interaction is normally done, you think of smell and taste, vision and audition. This is the classical way of thinking it, and surely not smells and sounds. So we tested this very wild idea. Of course, my postdoc at the time, Leo Cohen, said it's a stupid idea, there's no way to do it. I agreed completely, but nevertheless, we gave it a shot, and what we found was actually quite remarkable. The experiment we did is recording from cortex, now the auditory cortex, and you play sounds to the cortex and build the receptor field of the auditory cortex neuron. Okay, so you get the receptor field of a neuron in auditory cortex. But then what you do is you blow air through the home cage of the mother, where the baby sits happily dreaming and sleeping, and you can blow air with the odorized air in the room through the nose to the mouth, and ask whether the neurons behave differently with and without the smell of the mother's own pups. Okay? So this is auditory cortex with and without the odor of the pups in the mother. Because none of this happens in the naive virgin.
So it's primary?
What?
The primary auditory.
Primary auditory cortex in this case. Okay, so for example, if you look at a naive virgin and you play this with frequency from 1 to 30 kilohertz, you see this neuron is responsive somewhere here. And when you play to this naive animal pup odors, the auditory cortex doesn't care at all. This is a neuron from a mother. So you see this neuron responds a little bit to 36 kilohertz with very few spikes. And when you turn on the odor, magic happens, and suddenly this neuron starts to fire quite a bit and very nice. Okay? This is yet another example. So this is rather sparse activation. Like I told you, neurons in cortex, neurons in auditory cortex are quite sparse, spontaneously and sometimes to sound activation. So this is where, when we play with the regular air, we repeat the same thing with air, then we put pup odors, and you can see suddenly this neuron started to spike, and you turn back the air, and the neuron recedes again. And this does not happen in naive animals, only in the mothers which are experienced with their pups. So what we claim is actually that odors not only do the classical odor things, but strongly interact with other senses, and in this case in an experience-dependent manner. Okay? The second part, so this was a neuron paper in 2011, and recently in 2015 we repeated the same experiment using 2-photon targeted patching by looking at the inhibitory neurons in the auditory cortex. So you can do this by lowering an electrode to a transgenic animal that has red in its inhibitory neurons, and record from the inhibitory neurons, fill them up, and you're sure that it's it's an inhibitory neuron, or you can record just next by in a non-red cell. And this way you can extract information from excitatory and inhibitory cells in the cortex. Okay? And what we found here, maybe just look at the top pattern first. When you patch an inhibitory neuron in a mother, again, so you build, let's see, you can build a receptor field of the cell, let's say from 3 to 80 kilohertz, and you get spikes around here. When you turn on the babies, the odors of the babies, the pup's odors, you get inhibition of this excitatory neuron in this case. Okay? But this is inhibition of an inhibitory neuron. If you patch a cell next door, which is an excitatory neuron, you see the opposite happen. So this neuron responds to some sounds here, but when you turn on the odor, there's a huge expansion of the receptor field of this cell. Yes?
Can it be some outlier neuron in the auditory cortex, which is supposed to be in the olfactory cortex?
No. What do you mean? First of all,
Maybe
you don't
we can-
find that in naive animals. That's the first thing. Okay? So this is not a basic design. And normally when you play odors, you don't get responses in the auditory cortex. This is a kind of a modulatory effect of the odors of the. So it's not direct input from the olfactory system. It goes through other circuits which we don't know yet where they are. But there is a very clear effect of the pup odors on the responses of the mother. And actually, if you look at in the first slide I showed you earlier, if you do it for the so this is not pure tones anymore. This is now we record the vocalizations of the pups. The pups have special cries that are singing in ultrasound. They call mommy, 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 mommy in ultrasound. And this is the responses of I think 15 or 16 neurons to the ultrasound. Okay, in mothers. Before and the same neuron after you put the pup on. So the first neuron, you see there's clear responses to the vocalization, and then there's inhibition, actually. Here there's excitation, or increase in activity. Here, increase, 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 increase. No change statistically, but if you look closely, you also already see changes before and after. Increase, decrease, increase, increase, increase. So, in at least these 16 neurons that we patched, the vast majority show an increase in the responsiveness to the cells, and our claim is that it's a disinhibitory mechanism. So the odor comes in and pulls the foot out of the brake. Okay, so it's disinhibition, and you can see all the real data here. So basically, this is with air, x-axis, with odor on the y-axis, and you can see that all the excitatory neurons shown in green are actually excited. The inhibitory neurons fall under the diagonal and are actually inhibited. And this is clear also for the spontaneous, for the evoked, the excitatory neurons on the right-hand side, inhibitory on the right-hand side, excitatory on the left, etc. Okay? So our claim is that odors go beyond the olfactory system, they interact with other sensory systems, and in the case of the experience of the mothers with their babies, when she smells the babies, the odorant actually impacts how she processes sound information. Okay, so this is the series of these two papers. Okay, and the last but not least, I want to take you back to the olfactory bulb and talk about plasticity there. This also connects a little bit to what you will hear about on Sunday. Great. Okay, so you know what, if maybe you don't know what drives my lab, we are interested in the thing that F1 you're excused, huh? You heard this yesterday. So I talked about this lecture yesterday. The main theme, you've heard me give lectures in conferences or something? No. So the main theme of my laboratory has to do with plasticity. We study the olfactory system and the auditory system and ask questions of what computations in the brain are changing after learning or all kinds of events. In this case, maternal behavior is one example. natural behavior. Pregnancy, mating, things like that, things of that sort. So we study sensory processing and the plasticity of the sensory processing. How do these change with time? So the question is, when the animal learns new odors, where can you find plasticity? You can find it not so much in the olfactory epithelium, that this is a quite dumb area of the nervous system. Nothing dramatically is changing there. But as you go already to the olfactory bulb, our claim is that you can find plasticity in this region already. I want to tell you just that this is under high debate. People would say that nothing interesting is happening here, and actually I've heard the talk last month by Richard Axel saying that nothing interesting is happening in the cortex as well, only in neocortex. I of course beg to differ, and I think very differently. And we have been in the last 8 years, I had a few projects looking at plasticity in the olfactory bulb. So just again as a disclaimer, you will find in the literature places where you can see evidence for large changes in micro cell activity following learning. So you can teach an animal some kind of odor discrimination task and find changes in, for example, the spiking synchrony between the neurons. So this neuron paper shows an electrophysiological evidence that he calls it associative cortex features in the main olfactory bulb. Okay, so the microcells themselves will change the dynamics based on the the sniffing cycles and how they are the spikes are synchronized one to another, and this has predictive ability. So if you just look at the synchrony between the neurons, you can tell if it's the animal made the right decision, wrong decision, etc. And you can see this after learning. Okay, so these types of papers show you that there are changes in the olfactory bulb. Okay, so there's much going on in the olfactory bulb. This is a very nice emoji I found. On the other hand, you will find papers that claim that there is no differences in the olfactory bulb. I will not elaborate on this paper because you're going to read all about it, and hear all about it on Sunday. But one of the things that they claim, that the very interesting things that we find in the piriform cortex, you cannot find at all in the olfactory bulb. So nothing much is happening in the olfactory bulb. Lots in this paper is happening in piriform cortex. So you can find evidence for different opinions of what's happening in the olfactory bulb. However, there's one thing that nobody argues about, is the phenomena of adult noogenesis. Who here, besides Noam, which can give the lecture instead of me, have heard about adult noogenesis? 1, 2, 3, 4. Okay, so we can go fast on this, okay? So basically, in the adult mammalian brain, neurons are postmitotic, and what you have in your brain is what you have when you were born. And when you will die, the neurons in your brain are the cells that you were born with. We're only losing cells a long time. And this was thought to be true for many years, but now we already know for sure that there are two brain regions in the adult mammalian brain where you have regeneration. One is the hippocampus, the other one is the olfactory bulb. Just disclaimer here, in humans we know that there's adult noogenesis in hippocampus, but the neurons that are coming to the olfactory bulb, actually there is a block on the highway of their path of migration, and in humans they divert their route and they make new neurons in the striatum. This is the finding from last year, made a lot of news. Okay, so basically the current state of the art is that there are two niches of stem cells, one in the hippocampus and one lining the lateral ventricle, called the subventriculosome. But there are actual stem cells there, and these stem cells continuously make new neurons. So even today, you have neurons in your brain that are born and migrating into the hippocampus and the striatum. In mice and many other animals, there's massive, massive innervation of new neurons into the olfactory bulb, and I will show you this. Yes, you have a question?
Does the future maybe remove these symptoms to other areas?
Yes, so when I write my grants, we no longer work on this. I have one student actually from the LSEC program that joined my lab last year to work on this, but he's the last one of the labs working on it. But all my grants are starting like this, you know. Nature left us a niche of stem cells, and if we will understand their secret, we will be able to replace neurons in Alzheimer's and Parkinson's. Okay, I don't think we will. The problem is, so the truth of the matter is that, yes, you know, nature left us a present. There are stem cells here that make new neurons and integrate into the circuit, which I will show you today. The problem is you need two to tango, okay? You need both the neuron to develop in the circuit, but you need the circuit also to accept it. So if I take the same neurons from the subapicular zone and I stick them here, they won't be integrated nicely, because the brain circuit here needs to accept them into the circuit. So you need to understand both sides of the story in order to fully complete the story. So the circuits in Parkinson, for example, where neurons are dying, we know which neurons are dying, it's not very easy to replace these cells. Okay, because the circuit itself doesn't accumulate, is not welcoming new neurons even in a healthy brain. So let alone in a sick brain. So the problem is much more severe than I initially thought. Yeah. But you know, in my grants, I tell them if we'll understand this process, we will. I no longer write this. Anyway, historically, there's a nice story around this because this used to be in dogma that many people still, you know, not of course, graduate students, but other students may believe that neurons cannot renew in the adult brain. And this was the dogma. The first who shattered this dogma was John Altman from Harvard University. And what he did is he used radioactive thymidine. Thymidine is part of the DNA. And when you inject radioactive thymidine, if a cell divides, the DNA opens because it replicates, and these things sneak into the DNA, and you can get radioactive labeling of cells. And when he injected this into rats, he found labeled cells in the hippocampus. So he published a paper in Journal of Comparative Neurology, not a very high impact paper, but it's an anatomical paper claiming that there is regeneration in the adult mammalian brain in the hippocampus. Nobody believed him, and this is a graph of the citations of this paper from 1965 when he published the paper. And you can see that the level of citation is about 2 or 3 per year, and these are his own citations. He is citing himself for 20 years. Okay, nobody believed him, told him. You can't do real microscopy, and the issue was that he found cells that are labeled by thymidine, but it was very hard for him to prove that these are actually neurons, because we know that other neurons in the brain do renew. Okay, blood cells, you know, we have many other cells instead of not only neurons, glial cells, etc.
Can you repeat how he labeled only new cells?
Yeah, if you inject the thymidine in, when the cell replicates in mitosis, the DNA strands open, and if there is thymidine around, and you can flood the body with thymidine, some of this thymidine will enter into the DNA in a replicating cell. Great. So this was in 1965, and this was, you know, people didn't fully believe him, and this thing got some attention in 1983 when Fernando Notenbaum found the same phenomena in songbirds. So there's an ultra cool story. I don't know who of you did Mangenonim with Mickey London? Not in biology? Never mind. So songbirds are great because they're like a model for language development, things like that, because they sing songs all the time and they learn it. They're born, they don't know these songs. And when a teenager bird grows up, the father takes the bird, fly in the forest, and the father teaches the teenager to sing for the female. And all this crystallization of the song is a beautiful story. It's a beautiful biological story, beautiful neurobiological story. And what Fernando found in 1983 is that this is correlated with neurogenesis. So there's high neurogenesis in the brain of the teenager, which is not newborn anymore. And this caught more and more attention at the late mid-80s.
Specific areas?
Yeah, it's very specific areas in the bird's brain. But the big breakthrough came with method, just a simple method that allowed to use, instead of radioactive thymidine, they use oxyuridine. Okay, so this is another marker of DNA replication for which you have an antibody. So you can actually use an antibody to stain these cells rather than the enzymatic reactions of the radioactivity. And this means that you can do double labeling. You can stain the neurons for BLD with green, and stain neurons with a neuronal marker with red. And finally, at 1987, they were able to nail it down that the cells that are replicating are actually neurons and not other types of cells. And this was the first very convincing evidence that John Altman was right, 20 years ago. And since then, this ramped up, and there's a big community of people studying adult neurogenesis. And I am one of them. Okay, so when I came to Hebrew University in 2005, and when I opened my laboratory, I was interested in the olfactory bulb, and still am interested in inhibitory control of the olfactory network. And like I told you, there are many, many interneurons for each projection neuron in the olfactory bulb, right? We talked about it when we talked about computations. What I didn't tell you is that about 30% of this population is continuously renewed and replaced in the adult animal. So if you look at specific neurons, they have a given duration of life. About 70% of these interneurons are there like any other neuronal circuit. You're born with them and you will die with them. But a good chunk of these cells are actually replaced. There's arguments about how much. Values lie between 18%, which is my paper, and some papers now take it up to 100% replaced. Of course, I'm right, but there is a debate in the field. Okay, yeah.
Same population, or it's just randomized 30%?
What do you mean?
Is there a subsection in which there's
Yes, 70% of these cells
are
intact.
They're not changing at all.
That's all. You will live with them, and the animal will die. 30% are replaced, and in fact, they are replaced. So there's not more neurons coming in, and there are more neurons in the animals. These neurons are replacing other cells that die. Okay? And I'm interested in different aspects. Okay? So when I came to open my lab, I was like a kid in a Toys R Us store. I couldn't know what I want to study. I like development. I'm interested to know how neurons develop, make synapses, etc. I'm interested in regeneration, like Mashma. Tal asked, okay, so I thought I can change the brain and cure Parkinson and regenerate make the blind walk again, and we can throw the wheelchairs. Exactly. So all the cripples will now walk again, etc. So this is regeneration. But I'm also interested in plasticity and olfactory coding and sensory coding. Okay? So I was actually quite amazed to see the size of this phenomenon, of this region, of this adult neurogenesis, and decided to ask what is the contribution of this to the network. So in order to study this phenomena, when we started, the idea was to use viruses to infect the newborn cells and to image them using microscopy. At that time, I was hired not because I'm so beautiful, surprisingly, but mainly because I came in with a very fancy method called two-photon microscopy. For you guys, every lab has a two-photon microscope, but at that time, I was the first one in Israel to bring this technology, and people were blown away and convinced to hire us. Okay? And the idea was to take a regular mouse, infect stem cells in the subventricular zone. The stem cells live here, and they are born, and they migrate long distances into the olfactory. So the main idea was to inject virus in a regular animal, wait a little bit until they grow up, and then, so the idea was to do two-photon imaging, to look at stem cells 10 days old, and then do two-photon imaging again and again, and to study how these neurons integrate into the circuit. So just so you get a feeling of how much is this, this is one of the slices of the brains I injected. This is a slice from a wild-type mouse from the olfactory bulb. Each dot here is an inhibitory neuron. This is the glomerular layer on the top. Mitral cell layer is here. You can't see them because only the inhibitory neurons are labeled. And what you can see here are tens and thousands of neurons. And these are all born in the adult animal. So all of these neurons I injected in the subventricular zone. And they migrated long distances to innervate. So what you see is a slice of an olfactory bulb of a wild-type mouse that was injected here with G. Okay? So it's really a dramatic phenomenon. All of these are new cells and synapses. And the question is, what is the contribution of these neurons into the network? Clearly there is structural plasticity here in this circuit. Okay? There's no argument about that. Okay, so this was the idea, that was the dream. I didn't have a real hypothesis about what these would contribute, but this sold well to grant agencies, so they brought me money. I could convince talented students to come to my laboratory, and we had to develop these methods to image the mice. So what we do is very similar to what you saw in the laboratory. You would implant windows, in this case over the olfactory bulb. You also glue this bar to the animal so you can hold it under the microscope. And we would just take a look inside the olfactory bulb and look at this process. So this is, again, sorry for the light and dark. This is an example of a window. Our record is 1 year to follow the same neurons and synapses in a mouse. Here you can see 9 months of an image, of a nice image of the two olfactory bulbs. This is a blood vessel in between the left and the right olfactory bulb, and that's just a regular snapshot from a still camera, from a regular camera. You can actually see that 3 months later, there's bone regrowing here. This is through a window that we took off the bone and put a window. There's a little bit of growth of the bone here, but generally in this animal the bone did not grow. And you can easily identify the same motifs of the blood vessels. This is 9 months. So you see the bone is growing a little bit, but still you have many regions in the bulb which are optically transparent, and you can do imaging through them. Okay? If you do low resolution imaging, you can see all these glomeruli beautifully. If you zoom in, then you can look at synapses and spine in the two-photon. You can go as deep as in the bulb as 500 microns. Okay? In the course, I think you went down to layer 2-3 in cortex, which is about 250 microns or so. And when you do that, when you inject a mouse, this is how it looks like. This is an animal under the microscope. Now again, this is 2016, so for you guys, live neurons in the live brain is like, I do this for breakfast. In 2005, I almost cried when I saw this in the microscope. Okay, so I was working with dead neurons throughout my PhD, and suddenly you implant a window, and what you see on the right is the cell body of the cells. You can follow live the dendrite and the synapses of these cells. Okay, so this was amazing at the time. Okay, you can see spines, etc. It's just a Z-stack. And what we did is we started to reconstruct these baby neurons as they migrated into the system, and we had a big theory at the time, not us, about how important are these newborn neurons, newborn interneurons, to the plasticity of the network. Okay, so we had this is actually a single author paper. I had to show my students that I'm still, I still have it. So this is a single author paper that I did with my own hands when I came in 2007 to describe, for the first time, our laboratory was the first one to describe these interneurons live. Until then, it was they were studied in dead tissue, so you'd kill the mouse and take it to the microscope. And we could study the dynamics of these cells, and we described that the cells, once they migrate and dock into place, they are like dancers. They send their dendrites all over. So actually, this would be one glomerulus, and this would be another glomerulus here. And these cells normally innervate 2 or 3 glomeruli, and they send their dendrites very, very dynamic. Okay? And at that time it was good because people had theories about how young interneurons are extremely important for the circuitry. I won't exhaust you with details because we don't have much time, so I'll skip all the synaptic stuff. Another observation we made, actually another laboratory in Harvard also made this, is, I blew the joke, is that we can stain synapses on the presynaptic side and the postsynaptic side. Most neurons that you know and learned about have a presynaptic component on the axon and a postsynaptic component on the dendrite. Okay? These neurons are very unique in the brain because they have no axons, only dendrites, and they have presynapses and postsynapses together. It's called dendrodendritic synapses. And on their synapse, they both talk to the microcell and get input from it. It's kind of a special type of inhibition. So we can basically label the presynapses and the postsynapses on these cells. And what we found is that when you follow the development of these cells, they first develop postsynapses. So they first listen to the synaptic input coming in, and only then they develop a presynaptic component. So the joke in the lab was that they're like Israelis. They first listen, and only later in development they talk. Like good Israelis, okay, in a conversation, you always listen and then talk. Okay, I won't exhaust you. This is experience dependent. Last thing that we did is to record from these neurons. Okay, a major missing link for about 6 years looking at these cells, we made all kinds of discoveries about their dynamics, and a big effort in the last period of the PhD of Yoav Livne, which is actually not an LSEC student, but from the biology, exceptional student, was to record from these neurons. And what we did is 2 photon targeted patch of these cells. Actually, you can see on the wall the same image that Yoav patched summer 3 years ago. And this is one of these baby newborn neurons in the olfactory bulb, and we were the first to describe their physiology. And I won't exhaust you with details. All I want to tell you is that we patched them and described their physiology during development, and we found that when they are very young, not only they listen because they have only postsynapses, but they also respond to many, many odors. So they're very promiscuous. And when they grow up, they become specialized to specific glomeruli. And this is also experience dependent. So if you teach them a given odor is important, the receptive field will be very narrow and specific to this receptor. So that's basically the story of the olfactory bulb. So for today's talk, we summarize. We're basically done. I told you about what's happening from the olfactory bulb to other brain regions downstream. And we ended up with this talk, which I could not complete, about our work of how plastic is the olfactory bulb. It's structurally very plastic, with lots and lots of dynamics. And I also told you that there are not only lots of interneurons, but lots of incoming inputs from neuromotor centers, etc. So I still am a big believer that this is a site of important plasticity.